Good evening, I am Dr. Coaxial, Associate Professor, Department of Mechanical Engineering. Today, I would like to give the lecture on the energy storage capacity and coaxial springs here. So, in this, we'll discuss about what do you mean by the energy storage capacity. Generally, these springs are used to store energy in the spring motors or absorb the energy. So, whenever the spring force and deformation is proportionate, the energy is stored, which is equal to the half P delta. How you got that relation? That is the gradually applied load acting on the spring. So that that is the area of the triangle which gives the total energy stored in the spring. That is given by the half P into delta. So where P is the load and delta is the deformation. And the helical torsion springs, the torque is transferred to a specific part of machine. That is the purpose here of the machine. Why a helical spring? And the torsion springs are designed to load the springs by torque about the axis of the coil. Here you are applying the torque about the axis of the coil here. And the torsion spring ends are designed to load the spring by torque about the axis of the coils. Here in the helical torsion springs, we are finding the bending moment, that is the P into R. It has a tendency to wind up the spring here. And it is resisted by the helical compression springs. Just you observe in the figure itself. And now, according to the theory of chord beams, we know the bending stress is M by A is equal to sigma B by Y. From that, we are finding the bending stress relation K into MB Y by I, where MB is equal to P into R. Here, K is the curvature in the stress concentration factor, can be obtained the relation at the inner fiber, 4C square minus C minus 1 by 4C into C minus 1. In case of circular wire, we are taking Y is equal to D by 2 and I equal to 5 by 6 to 40 power 4. We substitute all the values here so that the bending stress can be obtained by K into 32 P into R by 5D here. Here this is the force you are applying at the radius of the spring here. And the energy stored in the spring is given by the relation V equal to integral 0 to pi dm P square R square dx by 2A. P square R square into pi dm by 2A here. So the deflection is approximately R into theta in the force P direction that we should observe in the figure itself. So the angular deflection or the total angle of twist is obtained using the strain energy is equal to half P into R theta. That is equal to P square into R square into pi dm by 2A, from the theta equal to 64 P into R dm by E to the power of 4. So the bending moment is necessary for producing the unit angular deflection. From that, we can say how the helical torsion spring is very strong. So the stiffness of the spring can be obtained by K equal to P into R by theta, which is equal to U to the power of 4 by 6 to 4 dn. To prevent sliding friction, the small gap is provided between the coils which are supplied in the diameter of torsion spring decreases as the coil winds up under applied stress. The next one is the coaxial or the nested springs or concentric or composite springs. So what do you mean by the composite spring? So these are it consists of the two helical compression springs. One is inside the other. Just one should observe here in the figure itself here. So here, the inner spring is always having the left hand helix and the outer spring is having the right hand helix. To prevent coil locking, we are using the coaxial springs here. So what are the advantages of the concentric springs or the coaxial springs here? The more spring force can be generated inside a given space, thus it increases the load carrying capacity. Even one of the springs is breaking, the mechanism still is functioning. That is, the mechanism not stopped because of failing of the one spring. And there are no vibrations. These are the advantages here. But in the concentrically split springs, you have to design the springs in such a manner for the same material and the free length, the maximum shear stress created in the concentric springs are the same. The deflection is the same for both the springs, and the springs solid lengths are also the same here. Now, the analysis, you have to use some kind of notations. D1, D2, wire diameter of the outer and inner springs. Capital D1, D2, mean coil diameter of the outer and inner springs. P1, P2, axial force transmitted by outer and inner springs, and P is the total axial force. Delta 1 is the deflection of the outer spring and the inner spring here. And capital N1 equal to number of active force in outer spring and inner spring N2 we are taking, and see the radial clearance between the springs we are taking. So some kind of superpositions we are taking. On that basis, we are designing the study of the concentrated springs. The superpositions or the assumptions are the springs are constructed from the same material. Both the outer and inner springs are experiencing same maximum torque efficiency, and their free length is the same. These are all the assumptions that we are taking and deriving the designing the study of the concentrated springs. Free length is the same because both springs are deflected equally. Their solid lengths are identical here. And if both springs are subjected to torsional shear forces that are at their maximum, τ1 equal to τ2, so that we are using the relation K1 into 8P1 D1 by D1 cube equal to K3 into 8P2 D2 by D2 cube. And these are made up of the same tension, if the same material is utilized. So the strain index we are using to obtain the same stress concentration factor. So you will obtain the relation equating K1 K2, we are obtaining P1 D1 by D1 cube equal to P2 D2 by D2 cube. And if the deflection of the two springs are equal, equating the deflection so that you are getting the relation P1 D1 P1 by D1 to the power of 4 equal to P2 D2 by P2 to the power of 4. And both the springs are compressed completely. Solid length of outer spring equal to solid length of inner spring. Then you are obtaining the relation D1 N1 equal to D2 N2. And we are also assuming there are no coils which are not used. So the number of active coils and the overall number of coils are also equal. If we equate it there, we are getting the relation D1 N1 equal to N2. So from that equations, we are dividing the equation so that we are getting relation D1 by D1 equal to D2 by capital D1 by D1 equal to capital D2 by D2 equal to C, which is the spring index. The same thing you have to substitute the equation so that we are getting P1 D1 by D1 equal to P2 D2 by D2. So P1 by D1 square equal to P2 square by P2. So from that we are obtaining the relation D1 square into square by P2 equal to pi D1 square by pi D1 square equal to A1 by A2. What does it mean? That means the total load shared by is proportional to the cross-section area of the wire. And you have to design the concentrated springs in such a manner to find the radial clearance also by using the relation. Okay. And now C equal to, we are getting D1 minus D2 by 2 minus D1 by D2 by 2. Where to see the diameter clearance, here considering the design of concentrated springs. So 2C is equal to D1 minus D2. So by substituting the value of C is equal to D1 minus D2, the equations and solving, we are getting D1 by D2 equal to C by C minus 2. These equations we are using to find out the force transmitted by each spring. And finally, the leaf springs here. So the leaf springs are used for carrying the heavy load. They are using in the heavy machinery and in the lorries to carry the higher loads we are using. So simple example, driving board in the swimming pool we are using. The driver is the load at the free end of the cantilever, that is the driving board. The driver is starting to first spinning of the board, you see the feather itself. At the free end, it jumps using the board's spring motion. So the driving board is the leaf spring here. So in these suspension systems of cars, these are usually using the leaf springs. The most commonly variety, the spring is the laminated steel spring, which is known as the multi-leaf springs also. Here you see the parts of the spring here, master leaf, two extra length leaves, graduated length leaves, and here the leaves are held by means of the rebound clip and U-boards here, and center clips. And for the same thickness, leaf thickness T, a leaf equal to be with the cantilever beam, and the special case which we observe in the figure. And the thickness for the leaf of the width, that is the uniform decreasing from B, case B, case 2 here. So from the basic equation of the bending stress and deflection, the maximum stress, bending stress in the leaf spring will find. Data at the point can be derived by using the relations. So sigma B is equal to 6 by 2 square, and for uniform width and non-uniform width, sigma BL by PT square. Okay, thank you.